Section 2.3, we're talking about product and quotient rule, and we're going to finish off talking about some higher order derivatives, so the second derivative, third derivative, fourth derivative, and so on. So when we talk about the product and quotient rule, we're really starting to get into more difficult derivatives. So when we want to take the derivative of a product of two functions, the way that we get that derivative is the derivative of the first times the original second function plus the derivative of the second function times the original first. I like to shorten this up a little bit for to help me remember it, and I think of it as f prime g plus g prime f when I'm talking about the derivative of f times g. Right, so that notation isn't really entirely accurate, but it's a lot easier for me to remember just f prime g plus g prime f rather than have all the f of x's and g of x's in there. The quotient rule, we're taking the derivative of a quotient of two functions. So I have the numerator of this derivative is going to be f prime times g minus g prime times f, all divided by g of x squared. So again, in order to help me remember this, I usually think of it this way. So f prime g minus g prime f. Notice that it's the same as the way I remember the product rule, except that rather than adding them together, I'm subtracting them. So the product rule is f prime g plus g prime f. The quotient rule is f prime g minus g prime f, and I have a denominator of g squared. So I look at the first example, I can see that I have a product of two expressions here. I have f times g. So I'm going to take the derivative of that product, and to do that, I take the derivative of the first. Derivative of 4x is 4 minus the derivative of 3x squared. 2 times 3 is 6. X, I reduce the power by 1 and I just get x there rather than x squared. So this is f prime times the original g plus the derivative of g is 0, and then minus 2x, a derivative of minus 2x is minus 2. So the derivative of g, or g prime, is just negative 2 times the original f. And now from here it's just simplifying. I'm going to expand those out and then combine any like terms that I have. And I'm done with my derivative. An example of the quotient rule we have here, example 2. H of x is the quotient of these two expressions. So again, we're going to use the quotient rule here. I use f prime times g minus g prime times f. And that's all divided by g squared. So I've applied the quotient rule here. I'm going to expand this numerator. And then combine like terms. And when I combine those like terms, I can see that I have 40x minus 40x. They cancel out. I have two x squared terms, one in the numerator and one in the denominator. They cancel. I'm just left with negative 1/4. We're also going to discuss derivatives of other trigonometric functions. So we talked last time about sine and cosine. We also have all of those other trig functions. These we need to memorize. And we'll take a look at a few examples using those trigonometric functions. So I take a look at example 1. I have f of x equals x plus cotangent of x. So as I take the derivative of f here, I can take the derivative of the first term plus the derivative of the second term. The derivative of x is just 1. The derivative of cotangent of x, if I look up above in my notes, I can see the derivative of cotangent of x is negative cosecant squared. So my overall derivative is 1 minus cosecant squared of x. The second example is a little more complicated. It's sine of x, so it's a derivative from last lesson, but I have a quotient, so I'm going to combine a trig function and a quotient and take the derivative of that function. So when I do that, sine of x is my f, and x itself is g. So I have the derivative of f, derivative of sine of x is cosine of x times the original g, minus the derivative of the original g is the derivative of x is 1, so there's g prime times original f. So I have f prime g minus g prime f, all divided by g squared. I rewrite that in a little more neat way, but really there's not a whole lot I can do to simplify that problem. And lastly, I want to talk about higher order derivatives. And all this means is I can take a derivative multiple times. So if I start with one function, we've talked about taking the derivative. In this case, I just have a polynomial function. So I'm using the power rule to take the derivative of each of those terms. So I take the first derivative, I have f prime. So I get 12x cubed minus 15x squared plus 14x. Of course, the derivative of that 5 is just 0, so there's nothing there at the end of this derivative. I can take that first derivative and take the derivative of it. So I do that, it gives me the second derivative. Again, I just follow the power rules again and get the second derivative. I can continue on as many times as I want, so I can take the third derivative and so on. All right, so these are higher order derivatives. I have the original function, the first derivative, the second derivative, and the third derivative. Sometimes interesting things happen when we take the derivative of a trigonometric function. You can see here I start with sine of x as I take the first derivative, second derivative, third derivative. By the time I get to the fourth derivative, I've cycled back and I end up with fourth derivative of x equals the sine of x again. All right, in previous lessons, we've discussed velocity as the rate of change, or the instantaneous rate of change of the position. So it's the first derivative of the position, the velocity is. Acceleration is the derivative of velocity. Therefore, it's the second derivative of position. So if I were to try to take a look at these, I have s of t, that's my position function. My velocity function is equal to the first derivative of the position function. My acceleration function is equal to the first derivative of the velocity function. It's equal to the second derivative of the position function.